Alright, so today let's look at a problem that involves moments or couples. So when you have two forces acting in the opposite direction, it creates a couple or moment, which is a engineering term which simply means a turning effect, a force or a load that causes something to turn or twist. Okay. So we have an assembly here. There's a bar that is being twisted in this way, or you can think of this as a pipes that are joined in this fashion. And then you have these loads. You have a couple, so that means 35 Newton acting up, and then 35 Newton acting down on this bar, and then 50 Newton in that direction along the x direction, and an equal amount acting in the positive x direction. So what we've done is we've assumed the coordinate system xyz in this fashion so the origin is here. You can assume the origin anywhere, it really doesn't matter, but for our purpose we have assumed it to be the origin to be here. These are the x, y, and z directions. So how do we solve this problem? The problem simply requires us to find the resultant moment. Okay? So what is the final moment? What is the final twisting or turning load in terms of this vector ijk vector? So if you apply 35 Newton, let's imagine somebody's pulling here with 35 Newton, somebody's pulling down with 35 Newton, somebody's pushing here with 50 Newton, and then somebody's pulling with 50 Newton. Then eventually what's the net load? Okay. This is a simple problem, so basically let me first outline the steps. What we're going to do first is step 1. We're going to find the position vector. Find the position vector for AB. Okay, so AB is this section. This is AB. This bar here is AB. So we're going to find a position vector for AB, and then step 2, just multiply the position vector with the force, right? So moment is force times distance, right? This distance being the position vector. Okay, simple. All right, so before we do that, so we need to find the position vector, right? Position vector is quite simply, if you have two coordinates, like 2 points basically, point A is x1 y1 z1, point B is x2 y2 z2, then we just subtract them, we get a position vector. Right? We do b minus a, we get a position vector. Okay, so let's just write down point B here. Point B, and let's write point A. That'll be a little bit easier. Point A, what are the coordinates? Along x we have 0.35 meters, okay, comma. Along y it is 0, okay? Along y it is 0, and along z it is 0, right? Along z it is 0, along y, because that's the origin, this point A is, well, point A, let's assume here, is 0. Okay, so same way point B. Okay, so point B is here, right? So the distance along x is the same, right? So the distance along x is the same, 0.35. Distance along y this way, so basically this distance, that's what we need, right? So that is the 0.4 is the length of that arm, so this would be cosine of that 0.4, right? So 0.4 times cosine 30 degrees, and we'll calculate this later. Let's leave it like this for now, right? And then z, right? So z is this height here, and because this is 30 degrees, the height is half of 0.4, okay? Or 0.4 times sine 30. Sine 30 is half. So a little shorthand you can remember is the height, if you see this 30 degrees opposite to that, the height is half of the hypotenuse. So this is 0.2, okay? So we have A and B. So position vector of AB is, just do B minus A, okay? So 0.35 minus 0.35, and because this is a vector, we're going to start writing the IJK notation here. I simply means along x-axis, okay? Plus J is what? J is 0.4 cosine 30 minus 0, right? Oh, I made a mistake. So because this is back here, that is origin, it's going in negative y, so this should be negative. I'm sorry guys, so that should be negative, right? J, and K is again 0.2 minus 0, okay? It is good to write this hat, because sometimes what happens is, if you're writing 35k, don't think of k as kilo or something. So that's why it is good to put like a little hat for the vector. If you don't write, that's okay too, okay? So let's evaluate this. So this comes to 0i, so basically you don't have to write this, plus, or minus rather, because there's minus, so when you calculate that number, it comes to 0.3464, 0.3464 J plus 0.2 K. Okay? So that's our position vector. Simple. Now all we need to do is step 2, which is multiply the position vector with, once we multiply with one vector, the 50 Newton vector, and another time we multiply with the 35 Newton vector. Okay, so let's see. Okay, so RAB, so there's the position vector AB times, let's say so force 35, which is what, 35 along K, right? 35K. So that's why I don't think of this K as kilo, so I'll put a little hat there. Okay, so this is, I'm going to call this RAB. Okay, so so how do you well, see, 35K is basically, because we can't just simply write K, right? There has to be an IJK. Even though it is 0, we wrote this as IJK. So we're going to write K, this 35K also as 0I. So RAB times 0I plus 0J plus 35. Oops. 35K. Okay. Why 35K? Right? So this is along 35 along Z. We'll multiply the position vector. We'll multiply the position vector once with 35, and then we'll multiply that with 50, and then add those two couples together. Okay. So how do we multiply this? So you've probably seen this before. IJK, the position vector is 0, negative 0.3464, and then 0.2, and then, so this is the position vector, and then this is the RAB, and now we're going to write the force, which is 0i, 0j, and 35k. Okay, so multiplying this is how we do it. So so when you're on I, close out I, right, and multiply this times this minus this times this. So we have negative 0.3464 times 35, 6435, minus 0 times 0.2 is 0, but for completion I'll write it out in full. Okay, right, so that's that, minus, so the way it goes is we think of this as plus I minus j plus k. Okay, minus j. Now it's time to close this part, right, and then multiply these things. So 0 times 35 minus 0 times 0.2, okay, plus k. So now we close out on k and multiply the other ones. 0 times 0 minus 0 times minus 0.3464. Okay, right. The numbers, the I, j, and k, these, you know, they go after the number typically, but in this case I wrote before just so I can keep track of which ones I'm dealing with. All right, so let's multiply this together. What do we get? This basically becomes 0. So basically when you multiply 0.3464 times 35, you get negative 12.12. Negative 12.12 I. And if my arithmetic is wrong, I apologize. Please check after me. Okay. Minus, so that is 0, and that is 0, that is 0. So the whole thing is 0j, right? Plus 0, 0, 0k. Okay. So that's one moment. Now we need to take the position vector, multiply with the other force to get the other moment. So we did this. So we need to, so force is acting on that distance, so we got 1. So force is acting on this distance again, so we need to get another moment. Same thing, we'll repeat it. So here we have RAB times and then the force is what? 50I, and then there is, here it is only 50I, so no j and k, so 50I, right, it's negative 50I plus 0j plus 0k. Negative 50I because it's given, right? That's negative 50I because it's going in the negative x direction. Okay. All right, so negative 50I, so let's multiply this. The position vector remains the same. I'll just copy it from here. 0, negative 0.3464, and 0.2 here. I, j, k, and right, and then this is negative 50, 0, 0 this time. Okay. And here this is one of our results, so we'll highlight this. So we'll come back to this. We'll say first moment, okay, and then this would be the second one. Here I'm going to just go by, I'm going to do it quickly here. I, so this is 0 minus this is 0, okay, and then minus j, right, 0 times 0 is 0, minus of minus 50 times 0.2, okay, plus k, so this 0 minus this is negative 50. So negative 50 times negative 0.3464. Right? So when you do all of that, so the 0, the I is gone, the j, negative and negative becomes positive, and then there's negative left. So 50 times 0.2 is 10, so that is 10j, right? And then here minus and minus becomes plus, and then this minus is minus k. 50 times 0.3464 is multiply that by 100 and divide by 2, that's 17.32, right? 17.32. So this is our second second moment, right? So we call it first, we call this first moment, we'll call this second moment. So all the moments will add together. See, vectors, you can, all the vectors, all these moments, ijk, so this moment in ijk can be added to this moment in ijk. Okay, so let's add the i's together. So here I'll write 0i for completion. So adding these two together, you have minus 12.12i. Then add the j's together, so minus 10j, and add the k's together, minus 17.32k. Okay, so that's our final resultant moment. Okay, quick recap. We're asked, there are two couples acting, one in plus and minus z direction, other is in plus and minus x direction here. So we're asked to find what is the net resultant moment acting on this bar. So what do? We find the position vector first. That position vector simply means the physical position of this bar. Okay, we get how do we do that? We do b minus a, right? So we find coordinates of b, coordinates of a, subtract them, we get the resultant vector here. We get the position vector here, and then we multiply this position vector by the moments, right? Each moment, each force at a time. 35 Newton force, we apply that to this force times distance. Think of it like that. Force times distance gives moment, right? So we got that as the first moment, and then again force times distance is the second moment we got, and we added these two moments together. Okay, all right, that's it, and I'll see you all in another example.